Well, hello again, ladies and gentlemen. So let's move on and finish off our chapter on entropy by investigating the concept of isentropic efficiency. This is a way for comparing or calculating the efficiency of an actual device that may contain all sorts of irreversibilities. So the idea here is to calculate the maximum possible work that a device can produce, let's say, and then use the isentropic efficiency to calculate the actual work produced. So we calculate the maximum possible work a device can produce, and then we can calculate the actual work that a device that has irreversibilities in it. We calculate the actual work by using what's called the isentropic efficiency. Isentropic efficiency is basically a work or a power divided by a maximum work or power. Okay, that's the way we understand efficiencies. We'll talk about this in a moment. So we'll define isentropic efficiency for a work-producing device, a turbine. So remember, turbines are work-producing. We'll also calculate or derive an expression for isentropic efficiency for a compressor, which is a work-consuming device. And then we'll do an example involving isentropic efficiency for a turbine. We'll do an example today showing you how to use isentropic efficiency to calculate the actual work or power produced by a real turbine, one that contains all sorts of irreversibilities, okay? Okay, so let's get started here. Let's say we have two turbines. Well, actually, let's say we have a real turbine. So let's say we have a turbine. Okay, so we have some sort of a turbine. Now this turbine receives a certain inflow of something. Who knows what it is? Could be air, could be H2O. And so there is a propeller in here and it's producing a certain amount of work output. So this is work turbine or work turb. So this thing is producing some work. Now, let's say this turbine is adiabatic. So no heat transfer. Okay? And this turbine also is not only adiabatic, but it may contain irreversibilities. So there may be some entropy being generated inside. So this guy is not reversible. Not reversible. So there's some S gen going on inside. So this means S dot gen is greater than 0. So there's friction in there. Who knows? There's friction in there. What else is going on? Who knows? Now, if you apply the entropy balance to this thing and it's steady state, let's say, you will find that S dot gen is equal to m dot times S out minus S in. If you apply the entropy balance, there's no heat transfer, so the Q dot over T interaction goes away. If it's a steady flow device, the dSCV dt goes away. It's a single inlet, single outlet, so the summations go away on the m dot S terms. You take the S dot gen, you put it over on the left-hand side, and you get m dot S out minus S in. Or if you like, S out minus S in is equal to S dot gen over the mass flow rate for the working fluid. Okay? So if I draw the TS diagram for this device here, TS, let's say the inlet pressure, I've got an inlet pressure P1, I got an inlet temperature T1. I have an outlet pressure P2 and an outlet temperature T1. Of course, I have specific entropy too. I have S1 and I have S2. Okay, so I have inlet and outlet properties. Presumably this turbine is decompressing, so pressure is falling in the turbine, and so is temperature falling because I'm extracting work. So we have two isobars here. See, we have P1 and we have P2. And I may have a T1 here. So the inlet state, this is the inlet state number 1. And of course, I have an inlet specific entropy, S1. And then I decompress down to a pressure P2 and a temperature T2. So this is state 2 right here. And this is S2. So temperature falls. I extract some of the energy in the form of work. There's some irreversibilities inside. So entropy, specific entropy, also goes up. So this delta S from the inlet to the outlet is S dot gen divided by M dot for the working fluid. So the process looks something like this. For the air as it flows from the inlet to the outlet of my turbine. Okay? So that's what the process looks like for the non-reversible adiabatic turbine. Delta S is positive as we go from the inlet to the outlet because of entropy generation. Now let's do the same thing for the reversible turbine. Let's do the same thing for the reversible turbine. So this will be W dot turb, and I'm going to put reversible REV in the superscript. So this is reversible turbine. So this is the inlet, this is the outlet, and so we have a P1, T1, and an S1. We have a T2, a P2, and an S2. Okay, this is the reversible turbine. It's also adiabatic. It's also adiabatic. Now, if I apply the entropy balance to my reversible turbine, adiabatic, steady state, I get the same equation. I get M dot S out minus S in is equal to S dot gen. Now, if it's reversible, that means that S dot gen, no entropy generation, so S dot gen is equal to 0 if it's reversible. So S dot gen is 0. So this implies S out equals Sn, or S2 is equal to S1. So on the TS diagram for the reversible turbine, here's our two isobars here. P1 and P2 are the same as for my regular device. We're going across the same delta P. Same delta P. Note, delta P is equal to P1 minus P2 is same for both turbines. Okay, same delta P, same inlet temperature too. I got a T1. So here's T1. Here's my state 1 right there. And because it's an isentropic process, so S out is equal to S in, so this is isentropic. It's isentropic expansion in the turbine. Pressure's falling, so it's expansion. And so the process looks like this. So here is state 2 down at the bottom. So here's T2, and here's S1 equals S2. So that's what the process looks like for the reversible turbine. Vertically downward, state 1 to state 2. By the way, this state 2 is kind of a special state. It's the state for an isentropic expansion. So I'm going to put a little S right after the subscript 2. I'm going to put a little S here. And I'm going to call this state 2 sub S. So this is going to be 2 sub S. And I'm going to put a circle around it. 2 sub S means for the constant entropy process. So this sub S means constant S. Constant S. Specific entropy. S1 is equal to S2 sub S. Okay? Now the question is, which device produces more work? The turbine or the reversible turbine? Which devices are the most efficient? Devices with all sorts of irreversibilities or reversible devices? Well, the answer is, so let's make a little space for myself here. The answer is W dot turb is less than the work produced. So the work produced by the real turbine is less than the work produced by the reversible turbine. So the reversible turbine is the most efficient. So this allows me to develop an expression for efficiency. Eta isentropic, so this means isentropic, turbine, TURB, is equal to the work or power produced by the actual turbine divided by the maximum possible, which is from a reversible turbine. So the isentropic efficiency for a work-producing device, a turbine, is W dot turbine over W dot reversible turbine. Needless to say, the value for efficiency, note, eta isen turbine, needless to say, the efficiency for a isentropic efficiency for a turbine is equal or less than 1. If the efficiency is 100% or 1, we've got a reversible turbine. If the efficiency is less, we have an irreversible turbine. Okay, so let's write this one more time. Let's write this out one more time. So, review. The isentropic efficiency for a turbine is defined to be equal to the power produced by the turbine divided by the power produced by the equivalent reversible turbine, where P1, P2, and T1 are the same for the actual and reversible turbines. We have to start off with the same temperature and have the same pressure drop, else it's not fair comparing the two turbines. We're comparing a real-world turbine that operates between two pressure limits with the same inlet pressure with the maximum possible work produced by a reversible turbine. The TS diagram for both devices superimposed on the same plot. Temperature, S, same two pressure limits, P1, P2, they both start off at the same temperature, T1. The isentropic device goes from state 1 to 2 sub S. The real device goes from state 1 to 2. So S1 is equal to S2 sub S. That's for the isentropic device. And the real device ends up at S2. Okay? So this is how you compare the two devices on a TS diagram. One is reversible, one is not. And the isentropic efficiency is defined as the ratio of the work or powers produced. One last little thing. Two last little things. Note, we can also rewrite this efficiency in terms of specific work by dividing by the m dot of the flow through the turbine. So I can also write eta is equal to W dot turbine over W dot reversible turbine. I can write that as the specific work of the turbine times the m dot divided by the specific work of the reversible turbine times m dot. I guess I should have said here, m dot is also the same. So P1, P2, T1, m dot are all the same. So the m dots cancel and I get efficiency, isentropic efficiency is equal to the ratio of the specific works. Okay, that's if I don't know what the m dot is, okay? Needless to say, another note, if eta isen turbine equals 1, then the actual turbine is a reversible turbine. Actual turbine is reversible. Okay? In general, eta, isentropic efficiency will be less than 1. It can never be greater than 1 because no device is more efficient than a reversible device. Okay? The same thing can be done with a compressor. I'm not going to go through the whole comparison. Suffice to say that a compressor is a work-consuming device. Suffice to say that a compressor is a work-consuming device, and the reversible device, or reversible compressor, will consume the least work to pressurize the flow from one pressure to another. So the reversible compressor is the power-consuming device which consumes the least power between two pressure limits. So we can go through the same thing for a compressor, but we end up with different definitions and a slightly different TS diagram. So for a compressor, so this will be a work or power consuming device. A compressor is meant to pressurize flow. So I have a certain inlet pressure, temperature, a certain m dot, and of course, needless to say, a certain entropy, specific entropy. And then I have an outlet, temperature, pressure P2, an m dot, same m dot, and an outlet entropy, S2. And I've got a propeller in here, or some sort of a, so this is, we're doing work. So we have W dot compressor here. Again, I'm assuming an adiabatic compressor. The power consumed by the actual compressor compared to the reversible compressor is going to be greater. So the actual compressor, which has all sorts of irreversibilities, friction, unrestrained expansion, who knows what else is going on in there, will always consume more power to get to the same pressure for same T1, P2 minus P1, or if you like, delta P, and for the same m dot. So for the same mass flow, the same pressure rise, the same inlet temperature, the reversible compressor will always consume less power than the irreversible compressor, the real, actual compressor, okay? So we're going to define the isentropic efficiency for a compressor as the compressor power for the reversible device divided by the compressor power for the actual device. The actual device consumes more power to pressurize the flow. Therefore, the denominator is greater than the numerator. So this guy is always less than or equal to 1. Okay? If eta Isen compressor is equal to 1, then the actual compressor is a reversible compressor. So I put a little box around this and note that this ratio, so definition of isentropic efficiency for a compressor is always less than 1, equal or less than 1. And if eta Isen, if it is equal to 1, that implies the actual compressor is reversible. Reversible compressor. Okay? Let's draw the TS diagrams for the reversible and the irreversible or actual compressor. TS. Same two pressure limits. So we're going from P1 to P2. So pressure is going up as we compress. That's what a compressor does. Pressurizes the flow. Let's see here. So state 1 is right here. So the compressor, both the reversible and the real compressor, start off at the same temperature T1 and the same pressure P1. And of course, we have an S1 right here. The isentropic, i.e. least work consuming device, goes from 1 to 2 sub S. That's the isentropic or reversible path. And the real device goes from 1 to 2. State 2 has a greater specific entropy than 1. So S2 is greater than S1 for the irreversible actual compressor. So let's go over this again. We have two compressors. We have a real compressor, which is what we're interested in, and we have a theoretical isentropic compressor, which consumes the minimum work to pressurize what I'm trying to pressurize. The isentropic device moves vertically up on the TS diagram to get from P1 to P2. The real device has entropy generation occurring, and therefore S2 is greater than S1. Delta S from 1 to 2 is going to be positive, and it follows a path which is not vertical, but it's some sort of an angle from state 1 to state 2 with a resulting increase in entropy from the inlet to the outlet because there's some entropy generation inside. The real device consumes the most power to pressurize the flow. The reversible device consumes the least power. So we take the ratio of the two and we call it the isentropic efficiency. If your isentropic efficiency for some device is 1, it necessarily means that the device is a reversible device, reversible compressor, okay? Isentropic efficiency, the ratio of the compressible work for the reversible compressor to the real work for the actual device, that's for a compressor, and it is the opposite, it's the inverse for the turbine. The definition, I'm going to put a little box around this. The definition for the isentropic efficiency for a turbine is equal to W dot for the actual turbine divided by W dot for the reversible turbine. The reversible turbine produces the most power. The actual turbine produces the least power. So this ratio here is less than or equal to 1. Okay, so put a box around these definitions for isentropic efficiency. Now, this isentropic efficiency is actually used in a lot of places. If you go to work for Pratt & Whitney, Rolls-Royce, GE, and you go into their compressor and turbine divisions and start working on their jet engines or power systems, you're going to be dealing with calculating, estimating, using isentropic efficiencies to try to estimate the actual efficiency of your turbine or compressor that's inside your jet engine compared to the maximum possible or minimum possible works or powers for the isentropic or reversible devices. So the isentropic efficiency is a way to characterize how efficient your turbines and compressors are. Presumably, as an engineer, you want to get isentropic efficiencies that are as close to 1 as possible. A well-designed turbine or compressor will have isentropic efficiencies typically around 70, 80, probably not 90%. But as an engineer, you want to get your isentropic efficiencies as high as possible. A well-designed turbine or compressor has isentropic efficiencies somewhere north of 80%. That's a well-designed compressor or turbine. 80% or so north of that is considered good for a real-world device with all of its irreversibilities inside. Okay?